Just to give you a brief introduction, who Chelsea is, if you don't know her, but there's so much more that can be said, and I will tell you in this like one short paragraph. She's the Assistant Director of Computer Science and Electrical Engineering at Stanford University. And her lab is called Iris. So you will see a little bit of logo of an iris. And she studies intelligence through robotic interaction at scale. And it's a very actually fascinating field of research she will be telling you more about today. So thank you again for joining. She also spends time at Google as part of the Google Brain team. And yeah, it's my big pleasure that she's able to join us. She's also going to teach 2 classes, actually just in a couple of weeks, and you can find more information on the platform. One of them is graduate class CS224R, deep reinforcement learning, which starts on April 2nd. And the other one is a professional class, XCS330, deep multitask and meta learning, and it starts only, I think, next Monday, so it's very, very soon. So yeah, she's a wonderful instructor, wonderful person to have here. So thank you so much once again for joining.
Really happy to be here and excited to share some of our research on deep learning for robotics and specifically talk about where the frontier is. I'm also seeing some questions in the Q&A about there being a recording, and yes, this will be recorded, and the recording will be posted online. Great, so to get started, I think a great place to start is to think about what can robots do today? And we've seen examples of robots being able to complete fairly complex manipulation tasks, like being able to use a spatula to lift an object into a bowl, or really impressive videos from Boston Dynamics that allow robots to do really impressive maneuvers, such as kind of parkour-like maneuvers in environments like this. And the catch with these kinds of impressive behaviors is that first, in terms of the Boston Dynamics behavior, it's really undoubtedly impressive, but the behavior was manually tuned for this one particular environment. And the manipulation task of using the spatula to lift an object was trained using 15 minutes of data in that environment. And as a result, these behaviors are specialized to the environments that they were trained in and the environments that the behavior was tuned for. And this means that they're learning very narrow behaviors. That robots are able to perform complex maneuvers in narrow and controlled environments. And if you moved one of these different platforms a little bit, or if you gave the robot a different spatula, the behavior would ultimately fail. And so what I'm really interested in is how we might allow robots to actually go out into the real world in real environments like homes, offices, and so forth, and actually allow them to generalize, to perform intelligent behavior in those settings. Now, the tricky part is that we often train robots on a fairly narrow distribution, such as in a lab environment, and our goal is to be able to actually deploy these robots into the real world. And from the standpoint of machine learning, this means that actually generalizing to this wider distribution is pretty challenging because it was trained on a fairly narrow distribution with a small number of objects and a small number of environments. And so I think that there's 2 possible solutions, and I think that both of these solutions are really important. The first is to train on a larger and broader data set, try to think if we can scale the data that we're training robots on so that they can generalize fairly broadly. And arguably this training neural networks on larger data sets is one of the only recipes that's convincingly enabled in the wild generalization in other domains like speech recognition, machine translation, and image classification. And I think that this sort of thing will be really important and necessary to get robots to generalize. But I think that actually doing this won't quite be sufficient because I think that robots will inevitably encounter scenarios that are a little bit different than the scenarios that they're trained on, simply because the world is vast and has lots of different scenarios and lots of different environments and objects and so forth. And so the second ingredient that I think is really important is to think about how robots might also be able to generalize beyond the data that they were trained on. And I don't think we can hope to anticipate every possible scenario. So what we're going to look at is thinking about whether we can allow the robots to adapt at test time also. And if they're able to take in a tiny amount of experience at test time and adapt and learn from that experience, then they might be able to actually handle novel situations. So These two things, training on broader data sets and generalizing beyond the training distribution, are the two main things that I'll talk about in this webinar. And of course, this will only really be scratching the surface of this broader topic of deep learning for robotics, but should give you a pretty good sense for where the field is at today. Great, so first let's think about whether we can train robots across many different tasks. And the specific goal that we're going to focus on is to allow a robot to generalize to a new task that it wasn't specifically trained to do. And we're hoping to be able to do this by actually broadening the training data distribution. It's worth mentioning that there are some previous kind of research efforts that have tried to aim to allow robots to generalize to new tasks by, for example, enabling robots to generalize to new objects. But this was all trained and tested within the single skill of placing, or being able to generalize to new instructions, like new language instructions, but the new instructions will describe behaviors seen in the data. What we'd like to do is we'd like to take this a little bit further and be looking at allowing robots to generalize to different combinations of objects across a wide range of skills. So in terms of evaluating whether a robot can do a new task, we'll consider an example. So say the robot is in this scene, and we want to be able to tell the robot to place the grapes in the ceramic bowl. The robot in this case, the data it will have seen will be showing it how to place other objects into the ceramic bowl and how to do other things with the grapes, but it won't have ever seen a behavior that picks up grapes and puts it into the ceramic bowl, all in one trajectory. And to make things a little bit harder than that, we're actually only going to show it data from two different object sets, and it won't have ever seen any data of the grapes and this ceramic bowl in the same scene. Great, so then we're going to train it on 100 total sets of tasks where a task corresponds to kind of a specific behavior or trajectory. And these tasks are going to cover 9 different underlying skills, including things like grasping, placing, pushing, wiping, and so forth. And an example of these kinds of behaviors is shown in this video, where you can see examples such as placing the banana in the tray, dragging the ceramic bowl in a circle, and so forth. Great. So this is an example of the behavior that we're showing the robot. And this data was collected by using a VR controller to move the gripper of the robot in a particular way. And this is an example of 12 different tasks, but we're going to show a data of around 100 different tasks. And then once we collect this data showing 100 different tasks, we're then going to train a neural network policy that will take as input an RGB image and output a desired target position and orientation of the gripper. And so this policy will outputting 7 numbers, 3 numbers for the position, 3 for the orientation, as well as 1 number that corresponds to the opening and closing of the gripper. And this policy will operate at 10 hertz, such that it takes in a new image 10 times every second and predicts a new action. We chose this representation because it's maximally general. This sort of policy in principle could do lots of different tasks, depending on the data that you train it on. And importantly, this policy is also going to be conditioned on a description of the task. And we're specifically going to use language descriptions, and we'll use a fixed pre-trained language model to get embeddings of these instructions and then pass those embeddings into the policy. Great. So once we've trained this policy on our diverse data set, in order for the robot to generalize to a new task, the robot needs to be able to first correctly interpret the language command, second, visually identify relevant objects and distractors, and lastly, translate its interpretation of the instruction and what it sees into the robot's action space. And doing this all for a novel task is quite challenging. And as we'll see, we are actually able to get some degree of generalization. So for example, if we go back to the scenario that we looked at before, where the goal was to place the grape in the ceramic bowl, we gave it exactly that language instruction. And this is, again, a trajectory that it never saw in the data, and the robot is able to successfully complete the task. Similarly, and the thing that's really great is that the the robot isn't able to just kind of perform one task, but it's actually able to perform a number of different tasks that it didn't see in the training set, such as placing the banana on the white sponge, placing a bottle in the tray, and pushing a purple bowl across the table. Great, so now let's look at some of the actually quantitative experiments that actually evaluate the success of the policy. And in particular, we pre-selected a set of 28 tasks that are held out from all of the training data. And then we evaluated performance. And I emphasize pre-selected in the sense that we didn't kind of just pick the tasks that the robot worked on. We pre-selected a number of tasks that are all held out. All these tasks are shown in this big table right here. And we see that first, the robot has a non-zero success rate for 20 out of 28 of the held out tasks. The average success rate is around 32% over all of the 28 tasks. And so overall, this suggests first that there is really substantial signs of the robot being able to do tasks that it never saw any training data for, which is really exciting. But second, there's also considerable room for improvement in actually boosting this number from 32% upward. And then you can ask, where is the room for improvement in terms of the robot's ability to do these tasks? And so to understand where the room for improvement is, we evaluated the robot's performance with on the training tasks with either just like a one-hot ID for the task, as well as a language instruction for the task. And then we also evaluated, of course, this kind of 32% number, which is held out tasks with language conditioning. And first we see that if we actually evaluate the robot on training tasks, on tasks that it was trained to do, the performance is actually only 40%. There's only an 8% gap in being able to actually generalize to a new task. And the really larger gap is actually bringing up this 42% number up to 100%. And this means that really the bottleneck is just the robot's ability to complete the tasks in the first place. And we can actually look at kind of example failure cases of what the kind of robot does for tasks that it has a 0% success rate for. And I'm not sure if these videos are playing, but the kind of what these videos show is that even though this policy has a 0% success rate, the robot is actually really close to completing the task. So for the place banana in the ceramic cup, it actually knows to pick up the banana and move it towards the cup, but doesn't quite complete the last stage of the task. And for the second task of wiping the tray with a sponge, it also figures out that it should pick up the sponge and tries to kind of move towards the tray, but it isn't able to complete the very last stage of the task. And so this suggests that first, the 0% success metric is quite strict. And it also suggests that we just, that kind of just the ability to kind of control the robot arm is the major bottleneck in terms of completing these tasks. Great. So that was kind of a proof of concept that we can actually allow robots to generalize to new tasks, which is to start to generalize to new tasks, which is pretty exciting. Now there's a question of what if we scale up even more? So we were previously looking at around 100 tasks. The next step is we tried actually scaling this to more than 700 tasks using 130,000 trajectories or demonstrations of those tasks. We found that if we took the model from kind of the previous work that I mentioned and just tried to make it larger, that didn't actually necessarily improve performance. It seems like this kind of model architecture isn't able to actually absorb all of the information in this larger data set. And so what we did is once we scaled up this data set, we tried to actually see if we could design an architecture that is better at capturing all of the kind of detailed information in this larger data set. And so specifically, we designed what we're referring to as a robotics transformer. Similar to before, this is going to be taking an input images and an instruction and outputting an action. But there's a number of important components that allow this architecture to be better at absorbing lots of data. The first is that we're going to tokenize the inputs and the outputs into discrete tokens. We're going to use a transformer as part of this architecture And transformers have been widely used in natural language processing, and we find that they're actually a very effective architecture here as well for being able to leverage large amounts of data. And we'll, because our actions are now discretized with tokens, we'll use a kind of a cross-entropy style objective. And then for reading as input the images, we'll use a kind of a convolutional neural network called an efficient net, as well as a film architecture to condition on the instruction. This backbone of the network will be pre-trained, and then the output of these image embeddings will be tokenized with a token learner. I don't want to get into too much of the details here, but the biggest part here is that we're able to actually train this on a really large data set, on 130,000 episodes. This data set was collected across 13 robots over 17 months, covering more than 700 tasks. And what we found is when we actually evaluated this model on both seen tasks as well as tasks that were unseen, distractors that were new, and different background scenes, this model architecture shown in blue was able to kind of substantially outperform previous model architectures, including the architecture that we used in the previous work, as well as the Gato style architecture, which is an architecture developed by DeepMind. Great, so kind of the takeaway here is that if we scale up robotics data and train these big policies on these broad data sets, that allows robots to start to generalize in lots of different ways, including to new tasks, new distractor objects in the scene, and new backgrounds in the scene. We've also released the data from the first work, and there's a link available right here. Great, and then the other thing that I'd like to briefly touch on this kind of data set front is kind of this bigger level picture, which is that typically in robot learning research, the way that most research progresses is that first we will collect a data set for a project, then kind of complete that project with that data set, and then kind of don't use that data again for the next project. For the next project, we'll kind of collect a new data set for that project. And as you might imagine, this is really inefficient. And if you contrast this to what typical machine learning research does outside of robotics, typically one data set is collected once, like ImageNet or Wikitext, and it's reused many, many times by many different research projects. Or even better, instead of reusing the data set, we might reuse a model that was pre-trained on that data set and fine-tune that model or use embeddings from that model. And so I think it's really important for the kind of robot learning research as a whole to kind of move towards the second paradigm and try to move towards a scenario where we're sharing data and pre-trained models across institutions and, of course, across projects as well. If so, I think if we were able to share data and pre-trained models in robotics, then I think we could probably make a lot more progress on the really challenging research problems that come up here. And for example, if you imagined like what machine learning research, if machine learning research did what robot learning research does, and they kind of recollected ImageNet for every single project, that would probably be quite expensive, and probably computer vision wouldn't be where it is today. Great. So then I'll also briefly comment on like what's actually stopping us from sharing data across institutions right now. I think we have a little bit of a challenge in that I'll make an analogy, which is that I think that right now what the robot data landscape looks like is all these different islands in this giant ocean, where we have these different robot data sets that have been collected, and each of them is kind of an island that covers the whole space of possible kind of robot configurations, environments, objects, and so forth. And because these data sets are not super diverse, and because the whole possible space of robotics hardware and environments and so forth is so broad, this means that when another research project is kind of going to kind of try out a task and try out studying a particular problem, that research project usually ends up somewhere over here or over here. And this means that the data sets that have been collected before aren't useful for actually advancing that new robotics experiment or that new kind of task or problem or environment. And so one of the efforts that we're trying to do right now is to try to see, first, if we can collect data from many, many distinct environments, not just from one building, and also trying to see if we can have a kind of more centralized community-driven data collection effort that may allow us to unify some of the design choices so that first we can have a larger island, and second, we can kind of bring more people towards a single island by actually having everyone agree upon certain design choices. And so our goal is to collect data from lots of different real household environments. Our initial goal was around 50 different households, but we actually think that we might be able to significantly expand that with the kind of interest that we've seen so far. And we've been kind of developing a kind of integrating people from lots of different universities to try to contribute to this effort. And of course, if you're interested in contributing, feel free to reach out. Cool. So the first part of this talk, I talked about trying to train robots on broader data sets. And we saw that we can get signs of zero-shot generalization to new tasks and environments. But we should also probably try to share data across institutions and reuse data more frequently such that we can allow robots to actually generalize further and generalize to the extent that we see things outside of robotics generalizing well. Great. So now I'd like to also briefly talk about how robots might generalize beyond the training distribution. And we'll first look at this in the context of a simple grasping problem, where the training environment and the grasping policy was initially kind of trained in this sort of environment. It's kind of a bin. Its goal is to pick objects from this bin. And we're going to then try to test the policy in a number of different environments. And we're actually specifically going to pick environments that we found that the policy worked poorly in. This includes with harsh lighting conditions, with transparent objects that it didn't see during training, with the checkerboard background, as well as a physical change where we actually moved the gripper of the robot by 10 centimeters. And the policy in the training environment was fairly successful. It had an 86% success rate. And when we actually tried to put it under these new conditions, the success rate dropped significantly to 32%, 49%, 50%, and 43%. And one of the things I mentioned before is that it's really impossible to anticipate and prepare for any possible scenario that the robot might find itself in. And so what we're going to do is we're going to try to see if the robot can adapt to a small amount of data that was collected in this new environment. And so specifically what this will look like is we have our original data set collected in the original environment. We're going to use a reinforcement learning algorithm called QTOPT to train a Q function and a policy for grasping in this environment. This policy, again, gets 86% success rate. And then we're going to allow the robot to collect a very small amount of data, only 800 attempts, which can be collected in around a single afternoon in this new environment. In this case, this is the displaced gripper. And then we're going to take our Q function and simply fine tune it on this target data using a mixture of the base data and the new data. And then with this very simple fine tuning procedure, which is kind of very common in the rest of machine learning, we see that the policy can get around a 98% success rate, even though this kind of environment is completely different from what it saw during training. We kind of did a pretty fairly thorough quantitative evaluation there, looking at a variety of kind of physical changes and visual changes. I don't want to get into all the numbers here, but a few highlights is that first, we can see a fairly strong improvement in success rate, even after only 25 new attempts in the new environment. And here's actually a kind of a video of the policy in one of these new environments. And so in this case, with kind of an afternoon's worth of data, it's able to adapt to this new scenario and successfully handle this the kind of the physical change that we imposed on the robot. Cool. So this was all specifically in the context of grasping, and we saw that the robot can autonomously collect some data to adapt to a new setting. Now, what about kind of in general? Can we do this for any sort of robotics task? Ideally, what we could do is we could allow the robot to kind of autonomously collect data and adapt with that collected data. But there's a little bit of a challenge here. And the challenge is that if we collect a trajectory with reinforcement learning, the robot attempts the task. We collect one trajectory, and then we collect another trajectory, and so on and so forth. Typically in reinforcement learning with this sort of trial and error process, we assume that the robot can attempt the task multiple times. But one kind of subtle point is that it's actually unclear if we want the robot to autonomously adapt on its own, how it will actually get to the last state of a trajectory back to the first state of its next attempt to retry the task. And in a lot of simulation environments, you can just kind of reset the environment and allow it to attempt it again. But in the real world, if we want robots to adapt on the fly in their new kind of deployed setting, this sort of reset isn't possible. It might require a human to do something, and it prevents the robot from kind of autonomously adapting with a small amount of data. And so oftentimes what this looks like is, for example, if a robot is trying to hit a puck into a goal, this robot actually isn't physically capable of moving the puck back, and oftentimes a human will reset the puck between each trial. Or if the robot's trying to learn how to open a door, a person will kind of then close the door before every trial. And what ideally we'd like to be able to do is to allow robots to adapt without these kinds of resets. Now you might ask, well, maybe we can just run reinforcement learning algorithms without resets, just kind of run the same exact algorithms that we use when they do get these kinds of resets, and maybe they'll just still work. And so we tried doing that. So we took a very simple environment where the goal is kind of in simulation to have this fish move to a certain goal. And it turns out that if you give it a reset every 1,000 steps, it learns a performant policy at the task. But if you give it a reset only every 2,000 steps, it isn't able to get as high of performance over the course of learning. And if you give it a reset even less frequently, the robot hardly is able to learn a policy for the task at all. And so perhaps surprisingly, algorithms for reinforcement learning aren't well designed for this scenario where the robot is operating completely autonomously on its own. And this means that if we want to use these algorithms to allow robots to adapt during deployment at test time in the real world, they aren't going to be well suited for that. And so this motivated us to introduce this problem of single life reinforcement learning. And in contrast to episodic reinforcement learning, where you can try things again and again, or reset-free reinforcement learning, where you can kind of try to both learn how to do the task and undo the task, what we're going to look at is a scenario where we have some previous experience. And so the robot has possibly used these previous experiences to learn a good policy. Then the agent is faced with a new environment at test time, and its goal is to basically complete the task fully autonomously within a single episode without any human resets in that new environment at test time. And so kind of more succinctly, given previous data in a training environment, the robot or the agent has one life to autonomously complete the task in a novel scenario. We'll be starting to look at this in a very simple simulated environment. I'll show some examples in this half cheetah environment where, for example, during training, it just needs to run forward, and at test time, it sees a scenario that's completely different from anything it saw during training. Specifically, there'll be an obstacle that makes it harder to make forward progress. Great. And so then our goal will actually be to allow the robot to actually figure out how to adapt at test time within a single episode. Cool. So how do we go about approaching this problem? So first, what we did is we actually tried to run the robot in this environment. And its goal is to get to the green box. And it was trained in an environment without any obstacles at all. And what we're doing here is we're running the robot in a simulated environment, and we're fine-tuning it with reinforcement learning to try to have it update its policy and ultimately get to the green block. And ideally, kind of what we see here is it actually gets a little stuck. It gets knocked upside down, and it struggles to make forward progress and kind of get back up, first figure out how to get back up, and then figure out how to get over the obstacle to get to the goal. And so really the core challenge of this sort of single life reinforcement learning problem is to handle this sort of novelty and recover from these out of distribution states, such as being knocked upside down, without any sort of human intervention. And standard kind of reinforcement learning algorithms that run fine tuning in this environment won't encourage the agent to recover from out of distribution states. Now, what we're going to do is we're going to first encourage the agent to move towards the distribution of prior data, because this should help it figure out that when it's knocked back over, it should try to get back up, because that's a state that it saw in its previous data. But we don't want to exactly do that. These kinds of previous methods usually assume expert demonstrations, and they aim to match the entire distribution of prior data. And instead, what we're going to do is we're going to have it try to match the prior data, but do so in a way that's weighted by the estimated value of those states. And the Q function or the Q value function will estimate the desirability of the state. We can pre-train a Q value, our Q function, on the previous data, and then kind of try to match the prior data weighted by the exponentiated Q value of those experiences. And this will drive it towards kind of states that had good outcomes in the previous data. And we actually tried to run this on the same example that I mentioned before. And what we see here is that the robot is, again, trying to get over the hurdles. And ideally what it would do is it would kind of figure out how to get to the goal on its own, and we see exactly that. So it does actually flip over on its back at one point. But most importantly, it actually is able to figure out how to get back up on its feet and also figure out how to get over the hurdles and ultimately reach the goal. We also quantitatively evaluated this on not just the scenario that I showed you, but also a few other scenarios. And we found that in comparison to fine-tuning with reinforcement learning, this approach shown in yellow was more successful at completing the task at test time and was able to do so in a smaller number of steps compared to fine-tuning with reinforcement learning. There's also a lot of room for improvement. So I think that the sort of problem setting that we're introducing for the first time can be studied much further and actually allow, hopefully in the long run, robots to be able to adapt to new environments and handle novel states. Great. So to summarize the second part, I think it's important to allow robots to generalize to new scenarios that they didn't see during training by actually having them try to problem solve and learn at test time. And we saw some initial evidence that we might be able to do that by encouraging the robot to move towards previous data that it saw in the past. But of course, there's also lots of, I think, important research to be done before actually this being like a viable solution in the long term. And we're actively working on trying to deploy this onto real robots so that robots can try to adapt at test time rather than deploying a static policy. Cool. So yeah, overall, I talked about how we might allow robots to generalize broadly by training on a broader data set and also allowing robots to adapt beyond the training distribution. The last thing I'd like to touch on beyond generalization is that I also think it's important to allow robots to perform very complex and dexterous tasks. So we really focused a lot on generalization in this talk, but ideally, robots wouldn't just be doing very simple tasks like the very simple locomotion problem that I showed you, grasping, and kind of pick and place tasks. Ideally, we could also allow robots to do more complex tasks like folding laundry or tasks that require like fairly delicate maneuvers, like peeling a hard-boiled egg, for example. And I think to do this well, we need actually a data collection setup that allows robots to do kind of fairly complex tasks, and ideally set up that's low cost and has an easy to use teleoperation system. And so this is something that we've actually been developing. It's still in somewhat of the early stages, but we developed a low cost system that allows the robot to complete fairly fine grained manipulation tasks like unwrapping a piece of candy, like putting a cable tie around a cable, like zipping up a hoodie, and so forth. And the really cool thing about this setup is that the total cost of all 4 arms in this setup and other parts is less than 20K. This is less than the cost of a single industrial arm. We're also planning to open source both the hardware setup as well as some software that we've developed for this system. And it's also a lot of fun to play with. And I think it will help us actually move beyond simple pick and place tasks to some of the tasks that you can see here. Tasks that require dexterity, that require very quick motions, and so forth. And we also have some initial results that have found that for some of these tasks, we could actually train the robot to complete it autonomously. Cool. I guess, oh yeah, and the other thing that I'll mention here is these robots are quite low cost. I actually wasn't sure that these low cost robots would be capable of some of these things. And actually the manufacturer of these robots, Troston Robotics, also didn't know that their own robots were capable of these kinds of tasks, like putting RAM into a motherboard, for example. Great. With that, I'd like to acknowledge all the members of our research lab, and we have plenty of time for questions. Thanks, everyone.
Great. Thank you so much, Chelsea. Extremely interesting presentation. And I saw a bunch of questions coming in. We will try to get to as many as we can, but if you have some additional questions, don't hesitate to still use the Q&A box and ask your questions. Chelsea, I saw a number of people very interested in kind of the data sets you're using and what actually the data set is. Like, how does it look like?
Mm-hmm. Yeah, definitely. So in the first part of the talk, the data set corresponded to teleoperated demonstrations. And what that means is that we control the robot with a VR controller to try to match, we basically we program it to match the end effector of the robot to the position of, or basically take actions kind of mimicking the position of the VR controller. And during that process, we record images from the robot's cameras. We record the kind of position of the arm, which is measured by the joint angles of the angles of all the joints, as well as you can compute the 3D position and orientation of the gripper. And then we also record the action that was commanded to move the robot. And so generally, you can think of this as videos plus a sequence of low-dimensional sensor measurements on the robot arm. I guess, and then in the second part of the talk and some of the other stuff, it's all very similar. So we typically use RGB images as the kind of observation space of the robot. In some of the work where I was showing that very simple kind of simulated running task, that was all low-dimensional. It was just looking at the positions of all of the joints and so forth. But in everything else, we're using image observations. It's also possible to use depth, to use tactile sensors and so forth. There are various kind of upsides and downsides of different sensors. But we've found RGB sensors to be, or RGB cameras like webcams to be a really simple and scalable solution.
There was actually a follow-up question about the image processing, or like, during the training and experimentation. And you mentioned that all of these have advantages, disadvantages. So like, what is the advantage and disadvantage of the image processing, and how can we improve it?
Yeah, so in all of this work, we're basically training neural networks end to end. So we're training a single neural network to take as input the image and output actions. And so this means that there isn't any kind of computer vision pipeline that is trying to find objects in the image, for example. We're actually just kind of supervising the visual backbone of the model for the task that the robot is trying to complete. And one advantage of this is that it means that the robot's perception is optimized for the task. And the reason why this is actually quite nice is that if you imagine kind of a task of, for example, manipulating a water bottle, if you tried to develop a vision pipeline for that, you might try to exactly represent the 3D pose of the bottle and exactly represent the shape of the bottle. And inevitably, a vision system will have some failures. It won't be able to precisely estimate all of that. And you don't actually need all of that information in order to do very simple tasks like picking up the bottle. You don't need to precisely know the 3D positions. And by optimizing the perception pipeline for the task, it can basically learn heuristics and learn shortcuts and only represent the perceptual information that it needs for the task.
you. You mentioned a little bit about kind of sharing data and data being available. There was a follow-up question on that about envisioning like reusing data across projects and also institutions. What's kind of your intake on that? And like, could you kind of dive a little bit deeper on what you have said in the presentation?
Yeah, definitely. So I think that it's really critical to start kind of actually having us share data and pre-trained models ideally as well. My dream is to actually basically, at least in the short term, be able to develop models like analogous to BERT or analogous to GPT style models that people can use off the shelf on a robot. Of course, not for text generation, but actually for representing actions and representing images and so forth in a robotics pipeline and getting value from those kinds of models. So I think it's really important for the community to do that. There's also challenges. One challenge is that different people use different control stacks and different robots. Our initial efforts is we are, at least with the kind of the community-driven effort that I mentioned, we're trying to at least start with a single robot platform and setup, but then diversify in terms of environments, objects, tasks, and so forth. And that can at least give us a little bit of a certainty in terms of trying to, and it's a little bit less risky in that we can kind of focus on a platform that a lot of people in the community use. And then in the long term, I think it's really important to also start to develop pre-trained models that are a little bit more agnostic to the particular hardware, so that maybe you can't kind of zero shot handle a new robot, but you might be able to kind of spin up a new robot platform more quickly than if you were to do everything from scratch. Yeah, so I think that those are some of the considerations.
Perfect. Thank you so much. When you showed the last video, like with the the egg and like wrapping, like the kind of the candy and all these kind of things, there was a lot of excitement actually in the audience about that. And the follow-up question, or one of the follow-up questions, is about like how far are we in like getting this like further, or like making this actually the standard thing happening in the world, or like making it even applicable and like using it in practice.
Yeah, so we're really excited about that project too, and it's something that we're actively working on. We're actually going to be releasing a paper around that work probably 1 week from today, definitely within the next 2 weeks. And our initial kind of progress on that is actually we've been able to train neural networks to do some kinds of tasks like that, specifically a task like slotting a battery into a remote control, like being able to kind of tear off a piece of tape and put it on a box, and things like that, put a shoe on a person. But there's also lots of challenges. So first we are, like I mentioned, we're open sourcing the hardware setup. And so we're hoping that other people will be as excited about the platform as we are and actually kind of develop it or kind of buy it themselves and collect data on it and so forth. There are other challenges associated with getting like policies to do those kinds of tasks as well. One challenge that we've run into is that we've been able to do some tasks like kind of tearing off a piece of tape and so forth. But for other tasks, you need to be able to react really quickly to what's happening. So for example, the candy unwrapping, we actually were able to get a policy to do the initial step of like picking up the two sides of it and then pulling. But then the next step involves like finding where the flap is on the candy and then kind of opening the candy. And with a small amount of data, around 50 demonstrations, we found that the robot wasn't able to complete that next step of kind of finding the flap and then opening. We think that with more data, we should be able to handle that sort of challenge. But there's also a question of how much data you might need. And so we're also trying to kind of do some research along the lines of pushing kind of the robot's ability to react to these certain scenarios efficiently, and so forth. So yeah, also happy to answer more questions on the topic of that project.
What are some of the most promising approaches like you find very promising for building actually a robot with like true artificial intelligence? Like, would you be able to answer that?
Yeah, I think that the approaches that I talked about today, I think are some of the most promising because those are the things that I'm working on, and I wouldn't work on them if I didn't think that they were the most promising. So scaling up data, I think, is really important. Allowing robots and just generally systems for adapting is really important. I think that embodiment, I like studying robots because they're actually embodied in the real world, in the world that we live in. And unlike things like language models, they have to contend with a lot of things that come up in the real world that are really challenging. Another thing that I'll mention is that I've been talking a lot about scaling data, and I think that we also, a lot of the data that I talked about before was collected by a person controlling the robot. And I think that in the long term, we really need robots that can collect data autonomously on their own and kind of operate with autonomy in the real world. And that sort of autonomy is surprisingly hard. We find that agents and robots will get stuck all the time and kind of be not sure what to do. It's possible that we need kind of a parent to help the robot, just like analogous to how kids have parents that are helpful. But yeah, there's lots of open problems, and yeah, generally the things I find most promising are along the lines of what I presented today.
And if I follow up on that, maybe it's the same answer, like which ones are you the most excited about? Or like, what you actually hope to see maybe in the next, let's say 10, 15 years, something you're very excited about hoping to see?
Yeah. So I think that everything that, like all the ideas that I presented I think are necessary. Like I think that we need broad data sets. We need to adapt at test time to get robots that can operate in the real world. So I think that there isn't like any one thing necessarily that I'm most excited about, because I think that robotics is a really hard problem, and I'm a little bit more somewhat pessimistic, I think, in terms of like actually the kind of timeline for getting robots out into the real world. That said, in the next kind of 5 to 10 years, I'd love to see kind of results that show that we can start to push robots out of the lab into unstructured environments and so forth with these kinds of learning-based approaches, and also start to see kind of pre-trained models start to pop up that are useful and can be used off the shelf by lots of people.
Thank you so much, and apologies to put you on the spot. We also had some people who are a little bit newer to the field of robotics. Like, what would you advise them, like where to get started, where to learn more?
Yeah, definitely. I think that my biggest piece of advice is just like starting by getting your feet wet. I think that my first experience working, so I did a little bit of like Lego robotics in middle school, I guess, and that was fun, and definitely kind of introduced all the challenges that come up with building a system with different components, with sensors, with actuators. And that was fairly accessible. And then I also in college took a course on robotics, and it was a lab course where we kind of built a robot from scratch, built some sensors for it, and actually also also had the robot do various tasks and so forth. In our research, we mostly buy robots off the shelf and really focus on the brain of the robot, which I think is really the bottleneck. I don't think we're that limited by the hardware. And fortunately, there are some robot platforms that are they're getting more and more inexpensive. So there are various like mobile robot platforms that have a few wheels. Like I think Amazon has a platform that called the Deep Racer that's a few $100s. And there's some other platforms as well. And yeah, I think that trying to, if that's something that's kind of within reach, then I think that, trying to actually just try stuff out on the robot is a great place to get started. Of course, another place to get started is to learn more about reinforcement learning. And as Petra mentioned, I'm teaching a course on deep reinforcement learning in the spring. And there's also just lots of resources online to explore these kinds of things.
Maybe the last question, because I see that, the questions still keep coming, but at the same time, like we need to actually make the stop at some point. Like, what would you recommend as those resources, Chelsea? Like, where to look further, where to find out what's happening in robotics in the field, like how to learn more, like any favorite blogs you read, like any favorite kind of websites you follow? What would you recommend?
Yeah, so let's see. So in terms of like tools, like one physics simulator that we use a lot is the Majoko physics simulator, and it's fully open source. And if you want to get started playing around with robots in simulation, that could be kind of a good place to start. I think there's some starter examples, and you can try to get the robot in simulation to do different things. In terms of resources for just kind of learning about high-level ideas in the field, Peter Abiel, who actually was one of my PhD advisors, he has a podcast called the Robot Brains Podcast, and that's a great place to learn about various experts in the field, including both academics as well as people in industry. And then, I mean, if you really want to dive deep, you can look at kind of robot conferences, like Robotics Science and Systems is a conference that we submit to a lot, and then also the conference on robot learning are both great. And oftentimes they have actually videos of the talks at these conferences in addition to the paper proceedings available online. And then, yeah, I mean, there's various course content that I think is great. And course content is probably actually, in some ways, like more educational and more useful than like conference videos, for example, because they're really aimed at teaching rather than being aimed at kind of sharing latest research results. So it kind of depends on what you're looking for.
Okay, perfect. Thank you so much, Chelsea. We will wrap it here. Thank you so much all for all the questions. We will try to kind of stay on and follow up on the ones that are open if we can answer them. But really appreciate your time. Chelsea, thank you so much for making the time to do this. And we will be making this recording available to you. So if you missed some part, we would like to rewatch, you can do that. So thank you, everybody. Have a nice day and stay safe.